And so for the last few examples, let's go through and consider these, the 1D wave equation first, and then the 2D wave equation after that. So we've seen the 1D wave equation. This is the following PDE. It's a squared times the second derivative of u with respect to x is equal to the second derivative of u with respect to t, where a is the wave velocity, or the wave speed. And this directly comes from, say, having a 1D elastic bar, and studying how disturbance is going to propagate through the elastic bar, specifically a longitudinal wave. It's going to travel through this elastic bar. And for an elastic wave, there are many contexts where the wave equation is useful, but for an elastic wave, this is equivalent to saying the time derivative of momentum, which is rho times ut, for a disturbance u of xt, has to be equal to the spatial derivative of the stress in the bar, which, if rho, the density, material density, and linear stress constant k are constant, this is the same thing as the second derivative with respect to time is equal to k over rho times the second derivative of deformation, u. So for elastic waves, a squared is equal to k over rho for constant k and constant rho. So just like before, we have a number of different boundary conditions that we can impose on the endpoints of the bar. And to make things a little bit different than the heat equation derivation that we just went over, I'll go through and impose some different boundary conditions here. Say the bar goes from 0 to L. We'll say that the spatial derivative of the displacement u at the endpoints, so at x equals 0, has to be 0. And we'll impose the same boundary condition at x equals L as well. This is for t greater than 0, or greater than or equal to 0, as well as the initial condition, which we have always have to specify to be a little bit different now because we have a second order derivative with respect to time. So we're actually going to have two separate initial conditions. In general, we'll have an initial condition for u and we'll also have an initial condition for the derivative of u. Where f and g are some suitably chosen functions. And the idea is pretty much exactly the same as before. But we're going to see, we'll get a difference in the t equation, which we'll still be able to solve. Step number 1 is looking for any solution of the form, any and all solutions of the form that's separable and when we plug into the wave equation, this gives us the equation. It needs to be satisfied is a times x prime prime times t has to be equal to x times t prime prime. Which, if we divide by x times t, this is the same thing as the equation x prime prime over x is equal to t prime prime over a squared times t, which, just like before, is the ratio of two functions of only x. And the right hand side of this equation is a function, ratio of two functions of only t. And therefore, the only way of satisfying this with two separate functions, a function of x only and a function of t only, is to have this entire thing be equal to some separation constant lambda. Which then reduces our problem to two separate problems. The first being the differential equation x prime prime plus lambda times x is equal to 0, and t prime prime plus lambda times t is equal to 0. And we have suitable boundary conditions, specifically that the derivative of u with respect to x and the derivative of u with respect to x at 0 and at L both have to be equal to 0. So if we take a second to look at what that is for our separable function, this is saying that u prime at 0, L, or I should say ut, du dt, at 0, L, has to be 0, which implies that x prime at 0 should be 0. And likewise, we get that x prime at L should also be equal to 0 from this boundary condition right here. So we have that x prime at 0 should be 0 is one of the boundary conditions on x, and that x prime at L be equal to 0 is another boundary condition on x. And so we have a suitable Sturm-Liouville problem that we can go through and analyze for the solution of x. So the next step then, so number 2 is going through and solving for x and for t. And just like before, if you analyze the various cases for the various possible values of lambda, you're going to see that the only non-redundant case is when lambda is positive, specifically when lambda is equal to some omega squared. The differential equation for x then is just going to be x prime prime plus omega squared times x is equal to 0, which has the general solution x of x is equal to a cosine of omega x plus b times sine of omega x. And just like for the heat equation done earlier, the other two cases give you either the non-trivial solution or solutions that are contained within this possible solution right here. So the only thing that's a little bit different now is when we go through and satisfy the boundary conditions, which deal with the derivative of x. So we take the derivative of x, which is negative a sine times omega of omega x, and positive b times omega cosine of omega x. And when we plug in the boundary conditions, we get x prime of 0 is equal to b times omega, which has to be equal to 0, which implies that b is equal to 0. Then we get x prime at L is going to have to be equal to, b is 0, so it just becomes negative a times omega sine of omega x equals 0, for which we're guaranteed non-trivial solutions if omega is equal to omega m, with omega m is m pi over L, where m equals 0, 1, 2, so on and so forth. And so our general solution for x is equal to a m times cosine of m pi over L times x, for m 0, 1, 2, so on and so forth. And for t, the differential equation is this right here, which also has the same general solution, but with, oh, I just realized there should be an a squared right here. Sorry about that. But that means that Tm of t, because lambda is equal to m pi over L squared, Tm of t is going to be, in general, some constant t m cosine of m pi over L times a times t plus some other constant em times sine of m pi over L times a times t, which means that the general solution um for any finite value m is going to be in, we'll call these constants a star because they're arbitrary constants, a star and b star. And we can call them whatever we want to call them. But so when we multiply xm of x by tm of t to get our general solution for the nth integer, or the nth natural number, you have that general solution to the wave equation is any function of the form am cosine of m pi over L times a times t plus bm sine of m pi over L times a times t times cosine of m pi over L times x. And so just like before, because this partial differential equation is a linear partial differential equation, we can sum up each one of these solutions where m equals 0, 1, 2, so on and so forth, to get that general form for the solution to the wave equation. It's going to be an infinite summation, 0 to infinity of functions of this form right here. And this concludes step 2 of solving the wave equation. And the last step here is to recognize this as a slightly more complicated Fourier series expansion when we look to the initial conditions. So we need to solve for AM and BM here. But as long as this series is uniformly convergent, we have that, we can do term-by-term differentiation and term-by-term integration. And so just like the wave equation, we'll start with the initial condition for u, the initial position of all of the points of the wave, the initial displacement, u of x comma 0, this is our first initial condition, is that it's the initial value for u is some function of x. And when you plug in t equals 0, here you get a naught plus the summation from n equals 1 to infinity of a n cosine of 0 is 1, so cosine of n pi over L times x, which is the Fourier cosine series expansion for the function f on the interval from 0 to L. And we know directly how to solve for this. Remember that in our previous lectures, this is a naught over 2. So this capital A naught is a naught over 2, which for the Fourier cosine series is going to be 1/2 2 over L times the integral from 0 to L of f of x dx, and an is going to be equal to just the Fourier cosine series an formula, which is 2 over L times the integral from 0 to L of f of x times cosine of n pi over L times x dx. And this gives us the solution for all of the AMs here. Oops, I should make this some M, just to be consistent with this notation right here. And this will also make AM as well, to be consistent with the sum. And we can do the exact same procedure here now for applying the second condition, the second initial condition. You do have to be careful, just like before, we need the series to be uniformly convergent so that we can do term-by-term integration, which gives us this result right here, and same thing now. To apply the initial condition for the t derivative of u, we have to take the time derivative of this function, du dt, which necessitates us doing term-by-term differentiation of this series. And this will result in the sum from m equals 1 to infinity of am times -1 times m pi over L a times sine of m pi over L at plus bm times m pi over L times a cosine of m pi over L at, all of this times cosine of m pi over L x. This is the general expression for the time derivative of this general solution using term-by-term differentiation. So we need this series to satisfy that property, but as long as it's uniformly convergent, we have that this then at t equals 0, or du dt at x t equals 0, the second initial condition is that this is equal to some function g of x. When you plug in t equals 0 here, you get 0 for all of these terms, and then 1 for all the cosines here. This becomes the summation m equals 1 to infinity of bm times m pi over LA times 1 times cosine of m pi over L x. And this is of the form of the Fourier cosine expansion for the function g of x. And to be a little bit more specific, we'll call this coefficient just bm, lowercase bm. So we have here an expression of the form summation from m equals 1 to infinity of bm cosine of m pi over Lx. And this sum is from 0 to infinity as well. Sorry about that typo. And remember, this is if we write out the first term here as b naught we recognize immediately that this is the Fourier cosine series, the even Fourier series for the function g of x, and there's no divided by 2 here, so this b naught is going to be the 1/2 times 2 over L integral from 0 to L of g of x, and bm is just going to be the normal Fourier cosine series coefficient, which ends up being 2 over L integral from 0 to L of g of x times cosine of m pi over L times x dx. And remember, we're not looking for the lowercase bm's, we're looking for the capital BM's here. And b naught actually ends up not mattering, because when you plug in m equals 0 here, b naught, you get b naught times sine of 0, which is 0. But bm for every value of m greater than 1, greater than or equal to 1, is capital BM times m pi over L A. So we get that bm is going to be equal to 2 over m times pi times a times this integral and we have an exact way of going through and calculating this these BMs in this infinite series expansion for our solution. You know that a naught is this integral, am is this integral, and bm is this integral right here. So let's go through and do this for a specific set of initial conditions. Specifically, we'll assume that the initial displacement is the function x, and the initial velocity is the constant function 3, so positive 3. This is for x from 0 to L. So using our formulas for AM and BM that we just derived in A naught, we get that A naught will end up being 1 over L times the integral from 0 to L of x dx, which is 1 over L times L squared over 2, or L over 2, once we go through and do the integral. For AM, this is going to be equal to 2 over L times the integral from 0 to L of x times cosine of m pi over Lx which, after doing integration by parts, ends up just simplifying to 2 times L over n times pi squared times negative 1 to the n minus 1. It should be m, not n. And then lastly, the BM. The BMs are going to be given by this integral formula right here. Which is just 2 over m pi times a times the integral from 0 to L of the initial condition for the velocity, which is just a constant function 3. And this integral then ends up being 0 because it's the integral of cosine of m pi times x over L from 0 to L. So the solution to the wave equation as a function of x and time in general for this specific initial condition, for these specific initial conditions, is the infinite sum where Bm is 0. This entire term in the sum is 0. And then Am for positive m, and I'll split this up into 2 parts. Sum from m equals 1 to infinity of 2L over m pi squared times negative 1 to the m minus 1. Plus our A naught, which is L over 2. And there you have it. This is the general solution to the 1D wave equation for these specific initial conditions. And remember, the initial conditions were not on U, but they were on the spatial derivative of U. du dx and du dx at both these boundary points. So if we go through and take a look at this, we see that this is exactly what's happening, right? With our initial condition here for x is this u equals x. The initial velocity is 3 for each value of u. Ut is 3 for each of the corresponding x values. And we have exactly, right, that the boundary conditions are also satisfied. The boundary condition here is ux is 0, the x derivative here is 0, the value is allowed to change as long as the other boundary condition is satisfied, and same thing right here as well, ux is 0 at L. I just did it for a bar of length 1, but right, this formula holds in general, and this process holds in general, which is amazing. So this is very, very, very powerful, what we're doing here. So let's see what this looks like in 2D. So for the 2D wave equation, we have to consider the following equation. C squared, lose a squared for the wave velocity, the wave speed, times the second derivative of u with respect to x, plus the second partial derivative of u with respect to y, and this is going to be equal to the second partial derivative of u with respect to t. So this is the partial differential equation, where a is the wave speed, and we're going to assume constant wave speed. We have some boundary conditions that we have to specify. Again, we're going to do this on the rectangle from 0 to b in x, and from 0 to c in y. And we'll just give this the simplest possible boundary conditions, which are u at 0, yt is 0, u at x, or at b, yt is 0, u at x, 0, t is 0, and lastly u at x, c, t is 0. Where again we also have two initial conditions. U of x, y at 0 will be equal to some function f of x, y, and then du dt also must be specified. We'll say that's some function g of x, y. And so this is our boundary value problem for the 2D wave equation. And we'll try out our solution procedure that we've talked about before. And it's very similar to the solution procedure for the 2D heat equation, only we're going to see that the Sturm-Liouville problems that we end up solving. For x and y actually are the same as the heat equation, but the T differential equation is a little bit different. So step 1 is trying the ansatz to look for all separable solutions of the form u of x, y, t is equal to some function of x times some function y of y times some function t of t and when we plug into our PDE, this ends up becoming a squared times x prime prime yt plus x y prime prime times t is equal to x times y times t prime prime, and if we divide out by x times y times t, we end up getting a squared times x prime prime over x plus y prime prime over y is equal to t prime prime over t. Which, just like for the 2D heat equation, we can solve by dividing by a squared. We can solve directly for then x prime prime over x will be equal to t prime prime over t minus, or t times a squared minus y prime prime over y. And because this is constant function ratio of two functions of x, and this entire thing is a function only of y and t, this is equal to some separation constant, negative lambda. And again then, this gives us that x prime prime plus lambda times x has to be equal to 0, and t prime prime over a squared times t plus lambda has to be equal to y prime prime over y. Which means that, just like before, this is a function of only t, and this is a function of only y. So the only way these two ratios can be equal to one another is if they're equal to another separation constant, negative mu. Which give three separate ordinary differential equations that have to be satisfied. X prime prime plus lambda times x equals 0. Y prime prime plus mu times y has to be equal to 0. And t prime prime plus a squared lambda plus mu times t has to be equal to 0. And we first go through and satisfy the Sturm-Liouville problems for x and y, where the boundary conditions u of 0 is 0 and u of b is 0, and that x of b and x of 0 have to equal 0, and the same thing for y. So y of 0 has to be equal to y of c is equal to 0 in order to satisfy these, all four of these boundary conditions. And just like I did in the first heat equation problem, you can go through and show then that lambda, the only non-trivial solutions to this this problem are when lambda is equal to lambda m, which is m pi over b squared for m from 1 to infinity. This works for any value of m in the positive integers. And same thing for mu. Mu has to equal mu times n, where mu n is n pi over c squared, for n equal to 1, 2, 3, all the way to positive infinity. Not only that, but you have the general solution for x is going to be x m, or yeah, we'll leave this the arbitrary constant up front as xm times sine of m pi over b times x. Y n of y is going to be y n times, and maybe xm and ym aren't the best constants here. See that these constants out front are arbitrary, just like before. They get kind of redundant. But then lastly, for each one of these values of lambda m and mu n, we have that the solution for t is going to in general be c m n times cosine of the square root of this times t. The square root of this times t is, call it, if I define omega mn to be the square root of lambda m squared plus mu n squared, or the square root of m pi over b squared plus n pi over c squared. The general solution for t is going to be omega mn times a times t plus some coefficient dmn times sine of omega mn times a times t. And you go through and solve this differential equation, second order differential equation for t. So when we multiply all of this together, we get that umn of x y t are the general solution for u, which is a multiplication of this xm times this yn times this tmn. It's going to be a mn cosine of omega mn times a times t plus b mn times sine of omega nm mn times a times t times make some more space here. Try and fit all of this onto one line. Sine of m pi over b times x times sine of n pi over c times y. So this is a solution to the wave equation for any value of m and n that are positive integers. And so as long as the sum that you get is uniformly convergent, the general form for the solution to the wave equation is going to be the infinite, the 2D wave equation is going to be the infinite double sum from m1 to infinity, n1 to infinity of these functions right here. It's a little bit more complicated than the heat equation. So this was step 1. Step 2 is solving the Sturm-Liouville problem. And step 3 now is going through and solving for the coefficients amn and bmn. Just like before, for the heat equations, this is very, very cool. We look at the initial condition here. U at x, y, 0 is some function f of x, y. This double sum, when t is 0, cosine of 0 is 1, sine of 0 is 0. It reduces to AMN times sine of m pi x over b times sine of n pi y over c. Which is the form that we saw previously for the two-dimensional Fourier series expansion of a multivariable function f of xy. And so using the process that we did in the heat equation, we get the formula that AMN is going to be equal to 4 over p times c times the double integral 0 to b, 0 to c of f of xy sine of m pi x over b sine of n pi x or n pi y over c dy dx. And this was gone over when I talked about the 2D heat equation solution. Up here. Right here when we solve for AMN. The form that you get is exactly the same. So this is really incredible, and not only is this incredible, but what we can go through and do is to apply the second initial condition for the derivative, the time derivative. We need to differentiate the time derivative of this expression right here, which is possible as long as this is a uniformly convergent series. And when we do this and plug in 0, you know that this is going to be equal to the initial condition for the time derivative ut at every single point xy, which is the function g of xy. When we differentiate this double summation and then plug in t equals 0, we end up getting bmn times omega mn times a times cosine of omega mn a t at t equals 0, which is 1, times sine of m pi over bx times sine of n pi over c times y. Which, after using our orthogonality relations, just like we did to get this formula for the AMNs on this sum right here, we end up getting the formula for BMN is very similar. It's going to be 4 over A times B times C times omega mn times the double integral from 0 to b, 0 to c of g of xy times sine of m pi over bx sine of n pi over cy dy dx. And there you have it. So this is the general solution to the wave equation, as long as f and g are nice enough functions to guarantee that these Fourier series are uniformly convergent. So let's go through and look at a specific example or two. The first example that we'll consider is f of xy equal to that piecewise function that we used before, which is 1 on a small box, small rectangular box inside this region right here. And we'll also set the initial velocity equal to 0. Because for this example, we went through and we already calculated the AMNs in the heat equation, or the 2D heat equation example. So for this piecewise box function, it's 0 on this rectangle and 1 on this rectangle. When we went through and calculated the AMNs, we found that those were equal to this value right here. And for this example, we'll also have that the initial velocity, we'll assume that it's 0 at every point. So that the BMNs are 0. And we'll take a look at what the solution looks like. So this is a plot, an animation showing that the solution for this initial condition, and you see very clearly that you get these propagating waves that are bouncing off the boundaries, because the boundary conditions are the displacement on the boundary is 0, and this is really incredible, very, very incredible, because we're seeing here that we can go through and solve this partial differential equation, and the solution that we're getting is very realistic. We're seeing a bunch of traveling waves that are reflecting and adding and bouncing off the boundaries here, all traveling at the wave speed of c for this example. And it's important to point out here that unlike for the heat equation, the wave equation solution does not have an exponential term in it, it has the cosine in it. So if there are problems with discontinuities where you have Gibbs phenomena, there may be inaccuracies if you just do a straight Fourier series expansion. And there are ways around this using, one way is using filters or a smoothing filter. I won't be getting into this in this class, but there are ways around this. But this is what you see here at the very beginning in the Fourier series expansion of the initial condition here, where you see the Gibbs phenomena, and you can even see this as well in as the waves travel around. And this is a little bit more apparent maybe if we look at a different example. So I'm going to use the initial condition from the heat equation example that we used for the second example as well. So we'll see that now. The Fourier coefficients for F end up being the same in this example as they were for the heat equation. And we'll use an initial velocity of 0. The Pn coefficients are also 0 as well. So here you see with this initial condition right here, and the solution of the wave equation ends up sending a traveling wave at a positive, the wave velocity speed c, and then you see reflection here, and then a reflection here, and superposition of the two waves, and then a third wave once both of these hit this boundary right here. And you can really see, because of the discontinuity here, the problem with Gibbs phenomena going on in the boundaries here of these discontinuous portions of the wave. But the general behavior of the wave is very consistent with the wave equation, just like before. So this will do it for this lecture. I hope you learned something and had a great day. Thank you very much for tuning in.